Magnitude of a vector in component form. Welcome, everyone. Today, we are going to begin a new topic, the magnitude of a vector in component form. To start our introduction, let's define what we mean when we talk about magnitude in the context of vector algebra. Simply put, the magnitude of a vector refers to its length or its overall size. Now, it is important to remember the fundamental nature of a vector. A vector is a unique mathematical object because it provides us with two pieces of information, both direction and magnitude. However, when we isolate the magnitude itself, we are dealing with a scalar quantity. This means it is just a simple number without any direction attached to it. You can think of it as a value that tells us how far a point has traveled or how strong a force is, regardless of which way it is pointing. As we move through this lesson, we will specifically look at vectors expressed in component form. In this form, a vector is written using what we call standard basis vectors, I hat, j hat, and k hat. These are just mathematical shorthand used to represent our movement along the x, y, and z axes, respectively. Understanding these components is the essential first step before we apply the Pythagorean theorem to find the total length, which we will explore in the next slide. Conceptual understanding. Now that we've established that magnitude is simply the size or length of a vector, let's look at the logic behind how we actually calculate it. You might be surprised to find that you already know the foundation for this. To understand how to find the magnitude of a vector in three-dimensional space, we are simply going to extend the Pythagorean theorem that you learned in 2 dimensions into the third dimension. Let's start with what is familiar. In a 2-dimensional plane, if we have a vector, let's call it r, expressed as xi plus yj, the magnitude is essentially the length of the hypotenuse of a right-angled triangle. Using the theorem, we calculate the magnitude of r as the square root of x squared plus y squared. Now, moving into the 3-dimensional space we'll be focusing on today, we apply that same logic. For a vector r, which now includes a third component, written as xi plus yj plus zk, we are looking for the direct distance from the origin, which is the point 0, 0, 0 to the point x, y, z. Just as we did in 2D, we are calculating the straight line distance through space. This brings us directly to the general formula we are about to derive in the next slide. The mathematical formula. Suppose we have any vector, which we will call r, expressed in its component form as r equals xi hat plus yj hat plus zk hat. To find the magnitude or the total length of this vector, which we denote by writing r between 2 vertical bars, we use the following calculation. The magnitude of r equals the square root of the sum of x squared plus y squared plus z squared. To be very clear about what we are working with, remember that x, y, and z are simply the scalar components. These represent the specific distances or magnitudes along the x-axis, the y-axis, and the z-axis, respectively. Now that we have established the conceptual idea of extending the Pythagorean theorem into 3 dimensions, let's look at the formal mathematical formula we will be using. In the next slide, I will walk you through a step-by-step process on how to apply this formula systematically. Step-by-step calculation process. Now that we have seen the mathematical formula for the magnitude of a vector, let's break down exactly how to apply it. If you're feeling a bit overwhelmed by the square root symbol, don't worry. Finding the magnitude is actually a very structured 4-step process. First, you need to identify the components. Look at your vector expression and pull out the individual scalar coefficients. These are simply the numbers attached to our I hat, j hat, and k hat, which we'll call x, y, and z. Second, you must square the components. Take each of those numbers you just identified and multiply them by themselves. So, you'll calculate x squared, y squared, and z squared. And here is a very important tip. Even if one of your components is a negative number, squaring it will always result in a positive value. This is a crucial detail to remember to avoid errors later on. Third, you will sum the squares. Take those 3 positive results you just calculated and add them all together. You are essentially finding the total of x squared plus y squared plus z squared. Finally, the fourth step is to find the square root. Take the principal square root of that final sum. Once you've completed this step, you will have found the magnitude. In the next slide, we are going to put this exact four-step method into practice, using a real-world example involving a drone to see how these steps work in a practical scenario. Real-world example. Imagine you are monitoring a drone flying in a three-dimensional coordinate system. We can represent the drone's position relative to its takeoff point, which we'll call the origin, using a position vector. In this case, the vector r equals 3i plus 4j plus 12k, and our units are in meters. Our goal here is to find the direct, straight-line distance from the takeoff point to the drone, which is essentially finding the magnitude of this vector. Let's walk through the calculation process step by step, just as we outlined in the previous slide. Step 1. First, we identify our components. Looking at our vector, we can see that x equals 3, y equals 4, and z equals 12. Step 2. Next, we square each of these individual components. So, 3 squared gives us 9, 4 squared gives us 16, and 12 squared gives us 144. Step 3. Now, we sum these squared values together. When we add 9, 16, and 144, we get a total sum of 169. Step 4. Finally, we find the square root. The square root of 169 is 13. To conclude our calculation, the magnitude of the vector r is 13 meters. In practical terms, this tells us that the drone is exactly 13 meters away from the origin. Now that we have covered the theory and the formula, let's put everything we've learned into practice with a real-world example. As we move to the next slide, I want you to pay close attention because I'll be highlighting some common pitfalls where students often lose marks during these types of calculations. Common mistakes to avoid. First, let's talk about squaring negative signs. This is perhaps the most frequent mistake students make. When you are extracting your components, as we discussed in the calculation process, you might encounter a negative number. For example, if your x component is negative 3, remember that when you square it, negative 3 squared becomes positive 9, not negative 9. Always remember that because you are squaring each term, the result of each square will be positive, and therefore, your final magnitude must always be a non-negative value. Second, be careful not to confuse the vector itself with its magnitude. As we saw in our drone example, the vector, which we denote as r with an arrow over it, is an entity that contains both direction and size. However, the magnitude, which we write as the absolute value of r, is just a single, simple number representing the length. They are fundamentally different mathematical objects. Finally, a quick reminder on the order of operations. Do not add the components together first and then square the sum. You must follow the steps we practiced. Square each individual component, x squared, y squared, and z squared, separately, and only then add those squared values together before taking the square root. Now, before we wrap up, I want to pause and highlight some common pitfalls. Even if you understand the formula, these small errors can lead to incorrect results. If you keep these 3 points in mind, you'll be well on your way to mastering vector magnitudes. Let's move to our final slide for a quick summary of everything we've learned today. Key takeaways. First, always remember that the magnitude of a vector simply represents its length. Whether we are talking about a drone's flight path or a force being applied, the magnitude tells us the size of that vector. Second, let's keep the formula at the front of our minds. For a vector r, which is composed of xi hat, yj hat, and zk hat, the magnitude of r, written as the absolute value of r, is equal to the square root of x squared plus y squared plus z squared. Third, it is crucial to remember that magnitude is a scalar quantity. This means it is just a single number, and because it represents a distance or a length, it must always be greater than or equal to 0. You will never encounter a negative magnitude. Finally, don't let the three-dimensional aspect intimidate you. As we discussed earlier when looking at the conceptual side of things, this entire process is actually just a direct application of the Pythagorean theorem, extended from 2 dimensions into 3 dimensions. To wrap everything up, let's review the key takeaways from today's lesson on the magnitude of a vector. If you have mastered these points, you are well on your way to mastering vector algebra. Great job today!